We can use polarization to measure sugar concentration. Here's how it works. You take two filters. The first one we call a polarizer. The second is the analyzer. The analyzer can turn. You place some sugar solution between the two polaroids, and you send monochromatic light through the first filter, through the sugar solution, and then through the second filter. That light becomes polarized after passing through the first filter. And the sugar rotates that polarization plane of the light because sugar is optically active. So the light is rotated like this. Next, what you do is you take this analyzer and you turn it, rotate it, until what you see out on this end is brightest. So you turn it to there. Then you measure how far it's been rotated. That's called the angle of rotation. And that angle is proportional to the concentration of sugar in the solution. So if your sugar solution, so it might be water and sugar together, if there's a lot of sugar in there, you will measure a larger angle. If there's not much sugar, it'll be a small angle. We can do this with bridges to test points of stress. With bridges, there's a trick. We have two filters which are now crossed. We don't turn the second filter in the case of bridges. You put the bridge in between the filters and you make sure your bridge is made of perspex, which is a material that's optically active. Perspex, just like sugar, rotates the plane of polarization for light. So monochromatic light is sent through. It's going to shine through all of this and strike a screen on the back. Now, there are many different rays of light passing through these two filters. Some rays go up high, some go down low. We're going to analyze two rays. The first will pass through an unstressed point, the second through a stressed point. So our first ray comes through. This unpolarized light becomes polarized. It passes through a point on the bridge that's not stressed. And so there's no rotation. At this spot along this beam or ray, the vertical light doesn't pass through the second crossed filter, and so there's a dark spot on the screen. Now let's consider a second beam or ray that passes lower through the bridge at a point where there is much stress. The unpolarized light becomes polarized, and then it's sent through here. And as it passes through the plastic part, the perspex, there is stress, and that light becomes rotated. Now, I've shown rotation occurring in the air. Actually, the rotation is just happening in the plastic itself. So on this beam, look at this. Because of the rotation, the light can pass through the crossed filter. And so we have a bright spot at this point on the screen. So we make a bridge of perspex, place it between two cross filters, send monochromatic light through the two filters with the bridge between them, and then when stressed, the perspex rotates the light's polarization plane. We see light and dark spots, respectively, where there are points of high and low stress. Light spots, bright spots, represent high stress. Dark spots represent low stress. The shade or brightness indicates the degree, the amount of stressing in the bridge. So we can use this to identify stress points by finding the bright spots or bright points on this back screen. Liquid crystal displays is the last example of polarization. This is really cool, and it could actually be on the test. Let's look at your iPad. Your iPad is made up of tons of tiny little pixels. Each pixel is basically like a fancy light bulb. Now, it's not any ordinary light bulb. It's composed of 3 subpixels. So now I've shown the 3 subpixels. Each subpixel produces one color of light: red, green, or blue, the 3 primary colors. When we combine those reds, greens, and blues from the subpixels, the one pixel, this one pixel on the whole, can produce any color at once by mixing the correct amounts of red, green, and blue. So let's look at a red subpixel. This subpixel produces just one color, red. The red mixes with green and blue to make others. And not only can the subpixel produce just red, but it's a little it's good. It's good at making this light. It can produce different brightnesses. Right? So that's the key, being able to produce different brightnesses. So if you want a lot of red in the color coming from the pixel, you make the red subpixel really, really bright. If you don't want much red, you make the red subpixel not so bright. Here's what a subpixel is composed of. You have a polarizer with a vertical axis, and then you have this liquid crystal material between, kind of like a block. And then you have a crossed filter. So the liquid crystal is sandwiched between the two. And lastly, there's a red color filter. And this is so cool. You're going to love this. We send unpolarized light from a backlighting unit. We send it through this whole thing. When there's no voltage applied to this crystal, the unpolarized light becomes polarized, of course, and then when there's no voltage applied, it just passes on through without any rotation. So when there's no voltage, the vertical light is blocked by this horizontal filter, and you don't produce any light out this end. On the other hand, if you take and apply a voltage to the top and bottom of this crystal, then now the vertically polarized light, when there's a voltage applied, rotates. And after rotating, it's able to pass through this horizontal transmission axis. And so now you have light out the other end. If you want to produce light out the other end, you just apply a voltage. If you want a lot of light, make it a big voltage. If you want a little bit of red light, make it a small voltage. Applying a voltage causes this liquid crystal material to become optically active. So that's really cool. Here's our overview. You've got your picture there. This is just one red subpixel. You put a liquid crystal between crossed polaroids, and you place a color filter against the second. You send light through the crossed polaroids with the crystal between, just like the bridge. When there's a potential difference applied to the crystal becomes optically active, and it rotates the polarization plane, just like we've shown, of the light. The intensity, how bright the transmitted light is, depends on the applied voltage.